people from a lot of different backgrounds, and I am pretty happy to get a chance to talk in this sort of more sort of governance and regulation oriented track. Although I'll be talking about technological tools, the main thing here is to understand the way in which the technologies that we are building allow us to sort of change the way people interact with each other, understand those interactions, and actually sort of use them for social ends rather than merely technological ends. In particular, we talk a lot about systems change in this community, and I actually am a big fan of this quote from Zen and the Art of Motorcycle Maintenance. I won't read the whole thing to you, but the gist of it is that if you have a sort of underlying understanding of the world and sort of sort of essence of how and why things work, then even if you take apart the system, it will sort of recreate the same outputs. And what we want to do is actually examine new configurations of technology and behavior and try to sort of induce new patterns, not just sort of take down the sort of, in a sense, the symptoms of those patterns rather than the sort of underlying processes. So we're going to be thinking a lot in terms of complex systems and understanding how we can affect change in the world. So as humans, we're constantly co-evolving with our own technologies. We come up with new ideas, we come up with new tools, we come up with new methods, we put them into practice, we build things, and we fundamentally change the world that we're interacting in, which in turn has effects on us. And so we want to actually examine these feedback systems from first principles and sort of better understand how what we create might affect us and how to create things that will affect us in the ways that we want. And I also enjoyed this quote from Hayek, which basically tells us that economics tells us more about what we don't understand than anything else. And it's humorous because, economics as a field has made a really big push to be, counted amongst the sciences in the way the physical sciences are, rather than sort of owning its normative elements and thinking about it in terms of the subjective. And in fact, I'll talk a bit more about this, but economics is also inherently performative. When you construct an economic model, you often induce that behavior. Maybe not always, sometimes it doesn't take hold, but it's not as simple as describing the world. Sometimes it actually creates its own description. And we have to be aware of that because it's exactly how we end up embedding biases and things. So whether it's machine learning algorithms being used to recommend products or sort of crypto systems being used to facilitate or mediate transactions between individuals, the way that we describe the world as working actually affects the way it works. And so we are going to be talking a bit about these systems, and I won't go through this in great detail. If you're curious about the details of this slide, I actually recommend a talk from Odyssey 2 years ago that I gave. The gist of this here is that we have layers of sort of technological and behavioral aspects, but they actually span the social, the economic, the technological, and the physical. And today we're going to be talking mostly about the sort of interaction patterns, agent behavior, and value flows in the context of systems that are inherently human. So we won't be quite as focused on the lower levels of data and computation, though there's a lot of the research and product development and tool development going on in this broader community. I'm going to be talking a bit about engineering, and I don't mean in the sense of software engineering. I mean in the sense of systems engineering or infrastructure engineering, things that we build for the benefit of the public. So in our modern world, our economic infrastructures, our data infrastructures, they actually share a lot with our physical transportation infrastructures, water, gas, etc. Things that are, they've been developed over time. They're more or less safe, at least in much of the world, and this is done because of the way that we've regulated and overseen the creation of sort of engineered technologies. Whether it's the governments or the communities, there are a set of expectations and norms around the construction of technology, and that those things are then viewed as sort of first and foremost for the benefits of the consumers of those technologies. So engineering isn't just about what you can build, it's actually pairing that with a responsibility to the consumers or constituents of the systems that you're instantiating. And so kind of coming to the point of this talk where we're going to talk a bit about mechanism design and data science, we're recognizing that whenever we create a model of a system, it's going to be imperfect. There's no way to represent something exactly as it is. And so whenever you make choices about how to encode or represent that system, whether it's feature sets in machine learning models, whether it's sort of economic principles at the micro or macroeconomic level, you're actually making subjective choices. And in particular, it's very common to use optimization paradigms, which personally a big fan of. I did quite a bit of work on optimization as part of my PhD research, but it's a paradigm that requires that we state an objective. And that choice of objective is in fact subjective. It's like a little tricky, right? We call it the objective function. What is your goals? What are your KPIs? What are you trying to achieve? But wait, who decides what those are and do they work for everybody? So there's an inherent sort of inconsistency amongst the objectives of individuals in society. Not that, all potential objectives are equal, but that at an individual level, it's reasonable to assume that people at the very least have different preferences over the set of things they might care about. And in the most general case, they might be doing things that appear entirely irrational to one person, but are totally reasonable in the local context of the individual. So we really have to be aware of this whenever we're designing systems that have data in them. Because the moment there's data, there's some subjective choice about its representation, about its goals, etc. So when it comes to actual design, we're really trying to build ecosystems here, whether it's an individual project that's creating an ecosystem for stakeholders of various kinds, or whether it's a ecosystem of projects who have feature sets that work together to achieve some broader goals, some enabling of activity that was maybe previously unavailable simply because the different efforts of one party and another couldn't be aligned adequately. It's very abstract and broad, but what I want to say with this slide is that we're recognizing the difference between the design paradigm and the sort of living, breathing thing once it's been released. And so there's a sort of ongoing process where there's a sort of very human, what I'm calling the ecosystem level inputs here, sort of operational requirements, human needs, wants, features, the stuff that matters to people, and there's the technical level requirements, the things that you can actually do, that you have the tools for, whether it's the technologies or the skills, team members, etc., to actually create the thing. So in some sense, you can think of it as design and construction. There are other ways to think about it, but I generally look at it as something where upfront, you need to know what's possible, what you're trying to achieve, who you're trying to achieve it for. And then when you've succeeded in developing something, you've passed certain types of checks, yes, is this thing going to be safe? Are people going to be able to use it without worrying about it? My favorite example for this is like a bridge. Bridges are really technical. They're very context specific. The bridge you need over one river or maybe over a highway, over whatever, it's going to depend on the distance and the climate and the sort of geographical conditions. Are there earthquakes here? Are there hurricanes here? And yet at the end of the day, you drive over pretty much every bridge without thinking about it because there's a sort of built-in expectation, sort of standards, norms, etc., that mean that if you're in a place where the transportation infrastructure is generally considered safe, you just drive over a bridge and you do not worry at all about what aspects of the technical design and maintenance of that bridge went into it. And so this is the kind of place that we need to get with our sort of digital, economic, and social infrastructures. And in this launch stage, we're kind of moving a little bit past the startup mentality where you're just saying, well, let me get it out there, and starting to add in a little bit more engineering thinking, like, is this safe for the consumers of this? And to be clear, it's not a battle between the mindsets. It's just sort of understanding that as something becomes increasingly sort of infrastructural, it's part of how people live, they don't have the time or the attention to evaluate it from first principles themselves. And so when we do the design of mechanisms that facilitate human behavior or the analysis of the behavior under those mechanisms, it's important for us to be thinking about it from the perspective of a user who's not necessarily going to be making a evaluation of the safety or the health of that infrastructure. If I go to Amazon and I search for something and it gives me a recommendation and I go buy that thing, there's a systemic effect here, right? There's a funneling of the attention of the users to a small subset of products and services, very much controlled by that centralized entity. And so then the question becomes, is that healthy for the economy at large to funnel the attention down in that way? Is that an appropriate economic policy from the perspective of the potentially very broad set of, creators, inventors, product developers, et cetera? And the answer can sometimes be, I don't know. I mean, it certainly reduces the space of things that people are buying, but it could also be doing a very good job curating. So it's not a black or white, good or bad. We're sort of asking, how does that mechanism relate to the individual and system level behaviors, and what are the goals of that system? So I break this down in terms of a very sort of cybernetics way of thinking, in terms of adaptive systems. Apologies in advance for the abstraction, but I want you to be able to apply it to a wide range of potential projects, from smart cities to power grids. So there's a lot of great tracks here. And so with these adaptive systems, we have a set of possible interaction patterns. These are the things that are allowed. They're legal, acceptable, valid in the software. It's just what you're able to do. And then given that you can do stuff, then people actually do things. Now, you could do a very small subset of the things you're actually allowed to do. Maybe the patterns that emerge are that you can do these 25 things, but people only ever do these 3. And that's totally fine. But this is now starting to separate the notion of can do and will do, or can do and does. And if you want to actually channel that effort, then you find that often there's automatic feedback. So if this system allows you to do certain things, but if you start doing a lot of something, maybe the designers think too much, there's ways in which that thing can become more expensive. Now, incidentally, things as simple as supply and demand curves already have this sort of adaptive feedback, although it's not inherently algorithmic. You start to see, if you have lots of buying of something, and if there's a fixed supply of it, then, or maybe it can become expensive to make more of it. Sometimes you see effects on price. You get feedback loops. Now, more generally, setting aside specific examples that emerge from the presence of a scarce good, you get to just programmatic feedback loops. So maybe if you're in that Amazon example, you say, this thing was coming up top, but instead of funneling more to it, maybe there's a saturation point, and you start, pushing something down. If it's always the response, there's not enough exploration going on, right? The policy is converging to a small subset. If you think that that's not a good system property, you come into this layer and you say, up to a point, this is good, but at an extreme, it's bad, and we can provide automated feedback that changes the behavior of the system. So this starts to cause multiple loops where you get state feedback algorithmically, you've got sort of human feedback through behavior, and so now things are starting to turn along, and you've got a system that's been, maybe it's been designed and it's achieving some goals because the state feedback is funneling the system towards some goals, and the game is changing in real time in response to people's behavior and the feedback loops. But what happens when the goals of the system change? And this is where the concept of governance really comes into algorithm design. No matter what, these lower 3 boxes had some sort of implicit goal, some subjective choice about what this is for and why. But that can change too. So if as a community, that thing that was being achieved collectively is no longer the goal, maybe some norms have changed, or cultural preferences, or who knows why, because the point is it shouldn't matter why. Through a participatory process, it needs to be possible to redesign both the set of things that are acceptable, and in a sort of traditional governance process, this is literally going back to lawmakers and trying to change the acceptable rules for participation in society. But in a software-mediated setting, this could mean changing these feedback loops, these algorithms that make decisions, or essentially change the rules or contextualize the rules. So this is a sort of generic way of looking at the way that our human behavior, our sort of mechanisms, our potentially dynamic mechanisms, and our governance processes interrelate. So I've done quite a lot of work recently on computer-aided design methodologies. As a sort of optimization and controls expert, we use all sorts of computer and data-driven tools to design pretty much every sort of decision-making policy that shows up in sort of robotics, large-scale cyber-physical systems, sensor networks. There's all of the technical data-driven decision-making. It kind of lives in this simple paradigm. You have some observations, you make some estimations, you make some decisions. Your decisions induce a change on the system, and then you make more observations and more estimations and more decisions, and systems evolve. Sometimes in very high combinations, which means that the decision-making in one subsystem can affect the state of another system, and there starts to be this complexity that emerges not from the things themselves, but from their interactions with each other. And this is an inherently challenging thing to deal with analytically. So we have this sort of modern scientific method that involves computation, where you run essentially what-if experiments. And you say, well, I really don't know what's going to happen. So I'm going to build a model of this system to the level of specificity that meets my needs with my current questions. And then I'm going to say, well, if people did these things, if they acted in this way, if the weather happened like this, what would happen? And I use the weather example there because this is how you deal with, again, like, buildings. So you're dealing with building a building in Miami, its ability to pass tests that are established for, say, hurricanes. Whereas if you're building a building in San Francisco, you need to deal with sort of validation tests related to earthquakes. And when we come to these social and economic systems, there's going to be even more things that we know we don't know. And so the paradigm here is something like a mechanism designer's workflow or a data scientist's workflow, depending on whether you're in a design phase or if you're in a phase where you have real data. And you're going through this loop that I call the engineer's loop, and you would associate this with people writing, say, Python code. And I'm going to give some examples of that, versus what I call a pilot's loop, which is a decision maker. It could be a politician, it could be an executive. These are people who are using the technical infrastructure that combines data and sort of systematic representations to ask questions, to make projections, and say, well, we think we might want to change this rule, but based on, our models, it shows that if we change this rule in this way, we might expect this range of behaviors. And the reason this matters, particularly in a governance setting, is we get into a lot of debates that come down to who you believe is got the right ideas about what will happen if you do something. It's what-if debates, but nobody knows. And if you know that you don't know, the best thing that you can do is explore the conditions under which you might expect those outcomes. So you don't have to always have debates of the form, well, I say if we, build this bridge over here, then the traffic's going to flow here, and then all of the people. So I went to undergrad at Dartmouth. So in Vermont and New Hampshire, you have people who commute across the bridges and live in one state, work in the other. And so you can imagine maybe somewhere up on the Connecticut River, there's a town considering building a bridge, and they're like, well, what's going to happen to our local economy? Are all the jobs going to move here? Are the people working here going to move over there? Well, the truth is you don't really know, but if you're going to build a model to sort of assess that, it would be really nice if instead of having some people in a think tank arguing it at everyone, you had little apps that people could say, well, I think that this, and this are probably more likely to be true. What does this model say about that? I know that sounds kind of far-fetched, but I actually think it's pretty close to what we're going to see in the coming decades in terms of at least informed democracy. I say this in part because so much of the individual objective, so much of the individual opinion is actually over the assumptions, not over the conclusions. So we want to move into a paradigm where people don't necessarily have to be expert coders, data scientists, or economists to be able to say, look, I live here, I know some stuff, I'm going to make my own assumptions, tell me what I can expect given what I think. And then I'm going to make my decision, not based on what someone told me is going to happen if we pass this proposal, but what sort of I've kind of found in my own little micro-scientific process. And so at least personally, that's what I want to see in the future. And it's one of the reasons why we built this software to allow people to basically code up their own models. So you don't even necessarily have to trust mine, right? I make one and I say, here, use this. And you say, no, I don't like the assumptions you made, even in how you framed it. I'm going to frame my own. So I want to code something up and have a look at it. So I'm going to give an example of a comparatively complex sort of mechanism design process. This is essentially a stock and flow diagram of a continuous organization associated with a continuous security as being launched by a company called Ferrament. Don't worry about the complexity here. Essentially, this is a bonding curve for a share of a future revenue of a new company. And this entity, Ferrament, designed this thing, and we did some computational experiments. And it basically got mapped out into a software model where you've got a bunch of decision-making layers, you have some mechanisms that describe the consequences of making decisions, you've got states, and you've got metrics. And so you can essentially write a computer program in CAD that encodes these three layers and runs a loop and sort of shows the system evolving. And so here's some example outputs from that particular experiment. And you can see token supplies. You can see some market confidences in a setting where the company is burning down its initial investment and hasn't yet taken hold in terms of new revenue generation. You see a sort of loss in market confidence, but they managed to, in this particular experiment, hit a sort of positive margin point, and they kind of turn around, the market confidence rebounds, and this is basically a statistics from, we ran 20-25 Monte Carlo experiments under a variety of different conditions, and the gist of it here is just to kind of give you a flavor for what sort of data science techniques make sense in a context where you have system models. So you may have real data that's observed that you can funnel into these models. You may have synthetic data representing cases of interest to you, but you can start to do things like this kind of trade-off analysis in the lower left, where because this is a commitment of future revenue for investment, you can actually see that early on, before the company sort of takes hold, it's bringing money in and it hasn't paid much out because it's not actually paying back its commitments from its revenue. And as time goes on, if they actually start generating a lot of revenue, then in fact they pay out much, much more than they had originally taken in. And in this particular design pattern, there's a way to kind of go re-private after you've sort of realized enough returns. You can essentially buy back these credits and close this thing out so that you're not essentially becoming arbitrarily behind, in the sense that you raised maybe, say you raised 5 million, and at some point, if the company grows, you could be paying out hundreds of millions in such an example, and maybe the company is going to buy back all of those rights to future revenue, essentially go re-private. Part of the design for the project, it's something worth reading about. I'm going to try to go to something a bit simpler, but I'm going to close out this discussion with what this looks like when you're talking about real-time systems. So thus far, I've shown you examples from design work. In order to operationalize these systems in the context where there's real data, you're actually synthesizing your models of the system dynamics with real observed data, and you're doing something that's a bit like an advanced version of an autoregressor. So much of the machine learning technology that is used for time series systems that are running is actually derived from work that had been done in robotics some 10, 20 years earlier, actually and more in some cases. And the topic is called system identification. So you have parameterized or sort of gray box models. They have some elements that you know how they work because you designed them or because they have physical properties. Or in the case of a cryptoeconomic system, you have formal cryptographic assertions about how the systems rules work. And so you can actually code those rules directly into your model, but then there are other elements that are black box, such as agent behaviors. And what you want to do is combine your system models with your observed data to create what are essentially digital twins or representations of systems that are fusion of the human understanding that allows you to look into the future and the data understanding that essentially gives you the vision of the past, and you combine them to something that allows you to actually make conjectures, projections, question and answer about what if I did this? What might I expect? And so this is a sort of, I would say, stylized architecture, but it's implementable. So I'm going to take a brief pause, but I'm going to talk about something a little bit more concrete in the context of the Odyssey Hackathon, and that's going to be smart cities. And we're going to talk about it using this term, cyberphysical systems. So cyberphysical systems are essentially the marriage of our digital systems with the physical systems in the real world, including ourselves. They have humans in the loop. They're inherently decentralized, even when we're talking about, these sort of power grids and transportation systems, the agents moving through the system, the energy moving through the power grid, the people building, maintaining these systems, they're not actually, sitting in one place. There's not a centralized decision maker. Even in the cases where these systems are controlled by centralized entities, the actual day-to-day decision making is still highly decentralized. You've got people going out to say, repair a substation. You've got people taking care of these things. And you really can't reason about them like they have a God's eye. There's going to be hidden information that's only available locally. You go and you look at the thing and see, well, what's wrong with this and how do I fix it? And I want to see us moving towards a more cyberphysical systems-like view of even the systems we think of as purely digital. So again, these very economic and social systems, they have very similar ontological properties to these cyberphysical systems. And so I strongly recommend looking into it. I'm going to do a review of a CAD model that I wrote yesterday. It's very simplified, but it's of an intersection. And one of the reasons that I have this slide here is to show that these systems are multi-scale. So we have this notion of a smart city. It's made up of components that can range from the transportation systems to the administrative systems to the sewer. Like, it doesn't matter. It's a big pile of systems interacting with each other, but you can start to decompose it. And if it's an inherently geographic system, then like a city, you can kind of break it down and look at subsystems geographically. And so here I've kind of grabbed a slide with some different neighborhoods from different cities and sort of represent them as graphs, so you can start to see the relationships between the sort of infrastructural systems. And we're going to zoom in and think about an intersection, and in particular, say, an individual commuting and like sort of what they need, sort of safety, efficiency, etc. And the example that I wanted to use today is a very simplified version of a intersection, but we have a model here which is going to involve commuters arriving at the intersection. There's both cars and pedestrians, and then we're going to do the mechanism design, or an example of a mechanism design for a traffic light. Because actually a traffic light is a policy. It's a programmatic one that exists there to simultaneously provide efficiency and throughput and safety for the people who are using it. And it's just one maybe node in a bigger transportation network, which is part of a broader sort of intelligent system, geographic location. And while models compose nicely and you can look at them in terms of relationships to each other, you always kind of have to pick some scope. And I wanted to make something tangible. So here we have a four-way intersection, and we're looking at both cars and pedestrians. And I've got this plot on the right. It shows some results, but I'm going to actually jump out and look at this in the notebook. So anyone who is particularly interested in playing along, I also made a Google Colab version of it, so I can actually go back here. If you were to go to GitHub mzargham/traffic light, there's this Google Colab link is in the README. So you would get something that looked like this, which is the top line is pip install CAD, which is the package I'm using here. And then you'll see this is more or less the same notebook that I'm going to shoot through on my local. But I'm not on the internet, so I will be using this version. So let's see if we can go to full screen. So, all right, so here's my intersection. It's got 4 corners, northwest, northeast, southwest, and southeast. And I labeled my streets northwest, east, and south. Very simplified, but still kind of fun. So I have lists of roads, lists of corners. I have a parameter which determines the rate at which the number of cars get through the intersection per period. So I have it set to 7. This is a list itself because you can actually run experiments where you sweep it. So if I could say, what if I had it so that maybe 7 can get through, or 9 or 12, the implication is that the light period is longer, but it's just a built-in tool and is the ability to control parameters and run experiments. So I'm going to construct a graph representation of this system where cars basically queue up on one of the streets and they want to go to one of the other 3, and the pedestrians essentially queue up at one of the corners and they want to go to one of the other 2, the ones that they can go to. Of course, they could also potentially go from one and then want to go to another. And I actually can represent this as a graph. So I use NetworkX, which is a Python package, to create a graph object. And so here now I have each one of the roads and the links to each of the others, and I have data embedded on this graph representing the flow of traffic, and I have I'm able to use this graph in my light policy to basically say which links are allowed at any given time. So these are directed edges, you just see 2 of them. Similarly, I have my graph for my pedestrians going from the corners. And I have a set of light patterns. So I don't have a drawing of this, but what I actually did was decide that I was going to model my light policy by saying which edges were currently on. And I described 4 what I'll call safe patterns here, where this first one is the east-west transit and the walking across the street east-west. And then there's the north-south corridor, and then there's the sort of turning one. So you kind of allow traffic to go across the diagonals, and so there's 2 of those. And so I came up with this, kind of on the fly. It was yesterday. We could design all sorts of different policies, maybe even, optimize over some real data about how frequently cars arrive, or even have adaptive policies if you have sensors that sort of show you, how long the queues are or whether cars are queued, that actually dynamically choose the light rules. But like I said, I actually want people to be able to play with this one, so I kept it as simple as I could. I can then map my light pattern code to a light object, which basically puts 0s and 1s on each of the links based on whether or not they're allowed at that time. And I set up initial conditions and essentially just let this thing run. So if you're interested, this notebook contains a bunch of business logic that describes the model of cars arriving and pedestrians arriving and stores them in a state object. It has the light policy defined and stores the current state of the light. And then it has a commuter policy, which actually in this case, I've simply modeled them as following the rules. But one of the really fun things about mixing the mechanism design and the data science here is that I can actually start to put policies in for the commuters that break the rules. And I could even create models of accidents or the frequency of accidents. So if you did 2 things that weren't safe, you could actually include business logic that says, well, if I try to turn right and you try to go straight at the same time, then there's a whatever probability of a collision. Well, what are the frequency of collisions as a function of the distribution of policies of the drivers, as a distribution of the design or of the light rules? And these are things where you can get a sort of abstracted representation that you think about, but then you actually need to merge it with data in order to really start to understand what's realistic or likely. And one of the interesting things about this is that although this is stylized, actual structural and behavioral analyses of traffic lights is a real thing. So although I've demonstrated in CAD as our tool, I had a conversation with an engineer from the New York State Department of Transportation about the way that traffic lights are managed. And one of the things that's really interesting is that in some places, traffic lights actually have reprogrammable microcontrollers in them. So there's like pretty low level governance of traffic where if you're having a high incidence of accidents, you can literally reprogram the light. And obviously, you can make bigger changes if it's for example, possible to put in a rotary or new traffic patterns at a higher level. And one of the things I like about this example is that it's very physical and tangible, but we're doing very similar things with mechanism design and data science in the context of our digital systems. They're inherently, you're allowed to do these things, subject to these rules. The system is going to change based on observations, cues, logs, machine learning policies that say, well, if you do a lot of this thing, then I'm going to give you more of that thing to do. So we're actually entering a regime where we actually need computer models of our computer models if we want to govern those things in a way that's facilitating the actual goals of the humans in the systems. Because otherwise, you get the algorithms, they do what they do, not what you want them to do. And sometimes it's actually really hard to even see what they're doing. Because the digital equivalent of a traffic accident is a lot harder to see, and the damage is a lot harder to detect. So if it's being harmful to human users, that's hiding somewhere in the data. And you need to have an understanding of what might be representative of that harm. You actually need to engage with people and understand what they want and need from their data systems. So from my perspective, this is the sort of future of governance and regulation where we have this digital infrastructure. And I'd like to invite you guys to play with the tools that we've built. They're integrated into the Python data science ecosystem on purpose. A lot of the equivalents of this that you could do in specific fields, they live in highly siloed software. So you can do it, but you might need a special MATLAB toolbox, or you might need a domain-specific software that has pre-populated embedded models of the specific domain that you're working in. But as we move into these digital systems, people are creating new things all the time. There's never going to be one big library for everything. And in fact, the experts of those systems are actually the product designers, the users, the people who actually are spending time thinking about those algorithms, those decisions, those usage. And we want to make sure that it's open and accessible. So this is an open source Python package, and I'm hoping that people will find more exciting and interesting ways to use it. And I'm not sure if anyone got the opportunity to open this up and run it, but this is even available through the Google Colab. So if you wanted to change it, if you wanted to mess with it, if you wanted to go to GitHub and download it and completely rewire it, please feel free. And more broadly, we're building out more examples, tutorials, interactive documentation, and sort of building a community. So that's pretty much the talk. I would sort of end on saying, if you think this kind of thing is interesting, feel free to talk to me later. I'll give you more pointers. And I'm hoping that people find it really useful at the hackathon, because one thing I've noticed about a hackathon is that when you're trying to come up with new big ideas, you're not going to be able to implement everything about it. So if you want to try out your idea and see if it makes sense, if the ecosystem you're imagining is, sustainable, or if it just dies out, or if it's a situation where, well, you need to onboard at least this many people, otherwise the economics aren't going to work out, etc. I strongly recommend whiteboarding it out, doing the workflows, building a model. And for something on the complexity level of what I just showed you, I literally wrote that yesterday. And I did it that way precisely so that I would be showing you something that I could honestly say was simple enough for you to do in a hackathon to explore a new idea. Because if the effort level's too high, it's not going to work out for this sort of exploratory design process. Anyway, so that is my talk, and thank you very much for attending.
Can you take any comments?
Sure.
Yeah. So the last point you were talking about in terms of the governance of the traffic accidents reminded me of a really interesting paper which was presented at the ACM Fairness, Accounting and Transparency conference last week, the week before. It's called Algorithmic Realism.
Okay.
By connection to the difference with the evolution from legal formalism to legal realism. We've got this kind of, we're setting up for a shift from algorithmic formalism to algorithmic realism, where you've got these algorithms managing these situations where there are risks and soft squishy bags of water might get hurt. And so it's very like an epistemological treatise, but the essence is like by comparison with say scientific realism, capitalist realism, but it's too late for us to perfectly administer and manage these things. So we say have to take a pragmatic approach.
And I don't even say that it's too late, it's actually strictly impossible. So I mean, one of the things that people tend to overlook is the fact that literally every model is a reduction. And that's fine because we need them to create the world. But if we impose on them this assumption of objectivity at the level of, well, if it's not right, I'm not going to use it, you are either excluding things that are really useful and helpful, or you're basically taking something and treating as if it's true when in fact it has real boundaries, and the fuzzy, messy boundaries are the places that you need to protect and understand. And the traffic system's a really good example of that, simply because we're not going to not have traffic lights. We're going to have them. We're going to understand that people are going to break the rules sometimes, and the frequency with which they break the rules is going to depend on the laws, and the laws are going to depend on some other process, and we kind of bound them away from each other, and we make some cautious assumptions, and sometimes we make some, well, what if this, and would this be better? And that's exactly the way that we need to treat our algorithms. And from my perspective, the most important thing we can do is recognize the right pattern matches. So whether it's power systems or transportation systems, et cetera, look at the places where algorithms or processes make decisions. And let's use those to inform our regulation, our decisions, our design. Yes?
Well, models, by definition, are wrong because of an abstraction.
Yep.
So it's a function, not a state of a model.
Exactly. So the key here, though, is that models are incredibly useful. The problem comes when you try to imbue them with this expectation of rightness or wrongness outside of the context of their purpose.
Well, that's what George calls some are useful, and you have to determine which are useful. That's basically. And
to whom and to what ends. But this is important, again, because we do have a little bit of a tendency right now towards this, what I would call hyper-empirical paradigm, which is fine. Like I've worked as a data scientist, I've worked on robotics, I love data. The issue is that data is like looking in your rearview mirror. You can't actually understand where you're going through it. You can really only take a model of the world, take it to sort of fit that model, however you've decided to structure it, and then you're making an inference about the future by extrapolating the past through a lens. And so, to your point, the sort of all models are wrong is incredibly important, because if you overestimate the predictive power of your models, you can cause harm. But at the same time, we need to find this balance between how we reason about and sort of use our inherently human, creative, subjective, elements to say, here's how we should think about the world, and then apply data, then come to a conclusion. Oh, sorry.
No worries. Overfit is a problem, so you try to simplify the model. But resilience is also a thing. So you're trying to optimize a certain system, which is what automation usually does. But you also, I think, need to have in some backup. Is there a way to model that, or to allow bias? Because the input is also problematic.
Right. So in a robotics context, in highly uncertain systems, you deal with this by having like a sort of separation of the things that you don't know, and doing basically multi-testing. So in an environment where there are a lot of assumptions necessary, you run experiments under a wide range of assumptions, and rather than getting something that's optimal in the sense that it scores the highest under some conditions, you get things that are the phenomena or the properties you want are present under the widest range of conditions. And so this is actually much closer to a resilience frame of thinking. Also, it's much closer to a sustainability frame of thinking. So you don't have a single KPI that you're maximizing. You might have a big array of KPIs, and you might have acceptable ranges for many things. Then you're looking for the solutions, which remain sort of in the healthy or desirable subspace for the widest range of potential conditions. That is about separating and staging out models. So you have a model which is a representation of the system, and then you have a scientific frame where that model is just a tool. So you take the core of the model, and then you abstract out parameters, assumptions, inputs, and then that decoupling allows you to create really well-defined experiments. And in fact, part of the reason the tool that I showed you exists is because we were trying to do this, and it was very ad hoc. And we basically built in Monte Carlo experiments, A/B testing, sort of input streams, parameters, et cetera, so we can do sensitivity tests, failure mode tests, et cetera. And it's exactly for the reason that you're saying. We wanted the simplest useful model that was a representation of the system, but then at the same time, we needed to have all of these other things that we'd say, in this experiment, let's try this over this range of different things, et cetera. But that's actually not a new concept. It's very much how we design sort of robotic and like the uncertain decision systems that live in admittedly a more technical field. They have this kinds of sensitivity testing and this kind of failure mode testing built into their design processes. It's just that those design processes tend to be a lot more involved than the ones that we currently use for software. Or, I ran a data science team for a while. Like, we churned out stuff fast, and the validation and verification procedure was so standardized that we automated half of it, and the actual overall monitoring maintenance of the system properties ended up being the main focus, because that was the thing that was left for our sort of subjective assessment. Like, is this really doing what we want?
Well, and with a lot of machine learning algorithms, black box.
I'm sorry.
Yeah, sorry. Is there any other questions from anybody else? I'm also happy to hang out and chat. Cool.